You remember wiring up a lemon to make a clock tick in science class. Copper on one side, zinc on the other, and suddenly electricity from fruit. But what if I told you your garden soil is just a giant lemon, and two buried metals can kick it into overdrive? In the 1840s, the father of the electric clock, Alexander Bain, powered machines and transformed plant growth with this trick, until the technology vanished without a trace. Today, almost nobody questions why. What really happened to the Earth battery, and could using it double your harvest, right under the nose of Big Ag? The answer begins where electricity meets dirt, and nothing in your garden will ever look the same. In 1841, a Scottish clockmaker named Alexander Bain filed a patent that would quietly rewrite the rules of electricity. Instead of relying on expensive chemical batteries, Bain buried two plates, one zinc, one copper, into the damp ground and linked them with a wire. The result was a steady current, drawn not from acid or salt water, but from the earth itself. This was not a parlor trick or a fleeting experiment. Bain's setup powered the world's first electric clocks, their pendulums swinging with energy coaxed from soil. His patent, British patent number 8763, described how two plates of different metals placed in moist earth could drive gears and electromagnets, with no need for winding or refilling. The earth, Bain realized, was its own battery, one that never ran dry. Bain's earth battery was not just a novelty for the workshop. It found its way into the heart of Victorian telegraphy, where the need for reliable, long-distance power was growing fast. Telegraph stations across Britain began to use buried copper and zinc plates to send signals over single wires, with the soil itself acting as the return path. This earth return method, inspired by earlier experiments in Germany, let operators stretch lines farther and cut costs. In Hyde Park and along the Edinburgh to Glasgow Railway, Bain's buried plates delivered a clean, low-voltage current, often around 1 volt per cell, enough to mark paper tape at speeds that left rival systems behind. These installations were not just theoretical. Engineers documented how aligning the plates north to south and driving the zinc deeper into the ground could boost output. Damp soil worked best. Dry ground meant the current faded, and the system needed careful tending. But when conditions were right, the earth battery ran for months without interruption. Bain's own notes and patent petitions from 1841 to 1843 describe a technology that was both simple and profound. Electricity harvested from the chemistry of the ground, harnessed by nothing more than scrap metal and water. Other inventors soon followed Bain's lead. United States patents from the late 1800s, like those of Daniel Drawbaugh and George Diekman, expanded on the idea, chaining multiple earth batteries together to boost voltage for clocks and telegraphs. The core principle never changed. Two dissimilar metals buried in moist soil could turn the ground beneath your feet into a silent generator. In an age before power grids, this was a revolution hiding in plain sight. Bain's earth battery quietly powered the Victorian world, ticking away in back rooms and under railway embankments. It proved that the earth itself was alive with current, waiting to be tapped. The story of what happened next, how this technology faded from view, starts with a simple observation. Wherever these metal plates lay hidden, something strange began to happen in the soil around them. Reports began to circulate among telegraph workers and local farmers. In the damp fields where copper and zinc plates sat buried beneath the grass, something odd was happening. Telegraph lines buzzed quietly overhead, but it was the ground itself that drew attention. A line of grass running between the hidden plates stood out, darker, thicker, and taller than the patches just a few feet away. There were no fertilizer sacks, no secret compost, just the silent presence of two metals and the slow seep of current through the earth. No scientific paper captured these changes. Instead, the story moved by word of mouth. A station master in Yorkshire pointed out the lush strip running alongside a buried telegraph return. A groundskeeper in Essex joked that the grass seemed to know where the wires lay. The pattern repeated itself across muddy embankments and country lanes. Wherever the ground carried a steady current, the plants nearby looked healthier and more vigorous, as if they had found a hidden advantage. Decades later, a Connecticut physician named George Starr White took notice. White was no ordinary country doctor. He spent his career chasing the invisible forces of nature, convinced that electricity in the soil could unlock new possibilities for farming. In the early 20th century, he began to promote the idea that natural earth currents, what he called telluric electricity, could be harnessed to boost crops. His lectures and pamphlets described experiments where weak currents channeled through the ground seemed to spark life in tired fields. White's claims were bold, but he was careful not to promise miracles. The evidence was scattered, a patch of greener corn here, a row of beans that ripened early there. Most of what he offered were observations and questions, not hard numbers. The newspapers of the day sometimes mentioned these strange effects, but always in passing. One agricultural journal from 1915 described a farmer who swore his potatoes grew bigger near a buried wire. Another clipping from the Midwest told of grapevines that seemed to thrive beside an old telegraph pole. The pattern was always the same. No controlled trials, no official endorsement, just a persistent rumor that something in the soil was quietly feeding the plants. For many, these stories were little more than folklore, but for experimenters like White, they hinted at a hidden layer in the life of the soil, a connection between electricity and growth that science had yet to explain. The question lingered: was the earth itself nurturing these plants, or was it all a trick of the eye? The search for a real mechanism, something that could turn these scattered reports into a repeatable method, would come next. Copper and zinc, when placed in moist soil, do more than just sit quietly underground. They trigger a chemical reaction that turns the earth itself into a living circuit. The science behind this is called galvanic action. Here is what happens. Zinc, the more reactive metal, begins to lose electrons. Those electrons travel through a wire connected above ground, seeking out the copper plate. The soil acts as the bridge, carrying charged ions between the two metals. This flow of electrons is direct current, the same type of current that once powered Bain's electric clocks and telegraphs. But in the ground, this current does something else entirely. At the microscopic level, the zinc plate acts as the anode. It gives up electrons and slowly dissolves, releasing zinc ions into the surrounding soil. The copper plate, the cathode, receives electrons and helps complete the reaction. The soil's moisture is essential. Water molecules, along with dissolved minerals and salts, enable ions to move freely. Without enough water, the current sputters and dies. In the right conditions, moist, slightly acidic soil, the voltage between copper and zinc can reach about 0.8 to 1.1 volts. It is not much, but it is enough to set off a chain of changes underground. This weak but steady current starts to break apart chemical bonds in the soil. Nutrients that were locked up as stable compounds, phosphates, calcium, potassium, begin to shift. The process is called electrolysis. As ions migrate under the influence of the electric field, some become more available to plant roots. It is as if the battery is unlocking a pantry that was always there, but sealed tight. Plants, it turns out, can sense this voltage. Their roots are not just passive straws sucking up water and minerals. Decades of plant physiology research have shown that roots actually respond to electric fields, a phenomenon called electrotropism. In controlled lab experiments, roots bend and grow toward the cathode, the copper plate, when exposed to even tiny voltage gradients. Some studies show that roots can detect fields as weak as 1 millivolt per centimeter. The effect is subtle in the wild, but in a garden with copper and zinc plates, the roots are drawn into the zone where nutrients are most mobile. The result is a double boost, more available ions in the soil, and roots that actively seek them out. This is not magic or wishful thinking. It is a documented response in plant biology. The field strength in a typical earth battery setup, about 0.5 to 1 volt across a few centimeters, matches the levels used in laboratory studies of root electrotropism. The current also changes the soil environment in other ways, shifting microbial populations and even altering pH near the electrodes. In the best conditions, gardeners and experimenters have measured voltage with a simple multimeter, proof that the system is working, even if the changes are invisible to the naked eye. The mechanism is simple, but the effects can be dramatic. With copper and zinc acting as silent partners underground, the soil becomes more than a medium for roots. It becomes an active player in the life of the plant, channeling energy and unlocking resources that would otherwise stay out of reach. By the dawn of the 20th century, the quiet current flowing beneath the soil was no longer the only force shaping agriculture. A new player entered the field, synthetic fertilizer, and it would rewrite the economics of farming. In 1909, Fritz Haber and Karl Bosch cracked the code for extracting nitrogen from the air, turning it into ammonia on an industrial scale. By 1913, the first Haber-Bosch plant was running in Germany, and soon the promise of cheap, abundant nitrogen swept across Europe and North America. What once took years of crop rotation or tons of manure could now be achieved with a single bag of white crystals. The fertilizer industry did not just sell a product, it sold a new way of thinking about soil. Advertisements from the 1920s and the 1930s promised record harvests and effortless abundance, all for the price of a season's supply. Agricultural bulletins, backed by government agencies like the USDA, began to promote what they called NPK, nitrogen, phosphorus, and potassium, as the essential trio for modern farming. The message was simple. Healthy soil was not something you nurtured over years, but something you could buy, spread, and repeat. Farmers, faced with the pressure to feed growing populations and compete in national markets, saw the appeal. Synthetic fertilizer was reliable, measurable, and most importantly, repeatable. Each harvest meant another sale. The economics favored products that ran out, not systems that ran forever. Where an earth battery needed only 2 scraps of metal and a bit of wire, the new model turned nutrients into a subscription. A permanent installation, like Bain's buried plates, required a one-time cost and offered no recurring revenue. But a bag of nitrate or phosphate guaranteed a customer would be back next spring. The shift was more than technological. It was cultural. Farming journals from the 1930s are filled with testimonials for chemical brands, side-by-side photos of towering corn and lush wheat, all credited to the latest blend. By contrast, the old stories of electric soil and buried plates faded into the background. USDA bulletins from the late 1920s dismissed electroculture outright and called it a curiosity with no practical value for the modern farmer. The science behind galvanic soil currents was quietly filed under fringe, replaced by the certainty of chemical analysis and standardized yields. No secret memos or corporate conspiracies have surfaced to prove a deliberate campaign against Bain's invention. The record shows something subtler, a market that rewarded the disposable, not the durable. As chemical companies scaled up production and government agencies standardized recommendations, the earth battery was left behind, not by sabotage, but by the logic of profit and the machinery of progress. The soil's silent current, once a marvel of Victorian ingenuity, became an afterthought in the age of ammonia. Yet the physics never changed. The same reaction that powered clocks and telegraphs still hums beneath our feet, waiting for a new generation to rediscover what was quietly set aside. The question now is whether the promise of free energy and living soil can find a place in a world built on consumables. The answer may lie not in the archives, but in the hands of those willing to test the idea for themselves. A backyard gardener stands over 2 rows of lettuce. One row has a copper pipe and a galvanized nail sunk into the soil, wired together above ground. The other row grows without any metal at all. After 4 weeks, the difference is clear. The electrified lettuce is taller, with leaves that spread wider and show deeper green color. A digital scale confirms the change. The average wet biomass in the electrified row is 38 grams per plant, compared to 26 grams in the control. That is nearly a 50% increase, not quite double, but a substantial jump. A multimeter probe touches the copper and zinc. The screen flickers, then settles at 1.03 volts. That is the same range reported by gardeners across forums and YouTube trials, anywhere from 0.8 to 1.1 volts, depending on moisture and soil pH. Growth curves plotted over the month show the electrified plants pulling ahead by the second week and keeping the lead. Volts matter, and the readout is consistent. The gardener logs every detail: soil pH, daily rainfall, and voltage readings. At harvest, a simple t-test gives a p-value of 0.04, just below the scientific threshold for significance. The numbers do not guarantee doubled growth every time, but they confirm something real is happening. The current is not just measurable, it is making a difference in living plants. Turning your garden into a living battery takes only a few simple parts. Start with a length of copper pipe or heavy gauge copper wire. About 6 to 8 inches is enough for most beds. For the other half of the pair, use a galvanized nail or a strip of zinc, also 6 to 8 inches long. These two metals are the heart of the system. You will need a piece of insulated wire long enough to reach between the copper and zinc, with a bit extra to keep the connection above ground. Push the copper into the soil on one side of the plant's root zone, about 6 inches deep. Place the zinc or galvanized nail on the opposite side, matching the depth, and space them roughly 8 to 12 inches apart. The key is to keep them in moist soil, because if the ground dries out, the effect fades fast. Strip the ends of your wire, then wrap one end tightly around the copper and the other around the zinc. Make sure the wire stays above the soil surface. This completes the circuit and lets you monitor connections for corrosion. Once everything is in place, check your setup with a multimeter. Touch one probe to the copper and the other probe to the zinc. You should see a reading between 0.8 and 1.1 volts. If the soil is damp and slightly acidic. For best results, log your voltage and soil moisture every few days, and replace the zinc piece if it shows heavy corrosion. With this simple arrangement, you are ready to run your own experiment and track the results season after season. Today, a simple copper and zinc circuit can still coax real voltage from your backyard soil. No patents, no permission needed. As industrial agriculture pushes ever more inputs, overlooked energy sits beneath our feet and is quietly measurable on any multimeter. The science is real, and the scale of what you can do is yours to choose. Sometimes the most powerful current is the one we decide, do I to reconnect? Share your thoughts or experiments in the comments below.